SwayamPrabha. Digital India. Educated India.
I welcome you to this lecture, to this module of flow through porous media. What we are discussing in the last class is what would be the Reynolds number for a porous media and how this Reynolds number can be used to find out the pressure drop. So, this is one alternative way to express pressure drop as a function of flow rate other than the very common, very useful Darcy's law. So, we are heading towards this set of equations that I mentioned before, this Kozeny-Kármán-Blech-Plummer equation and finally Ergun equation. So, to arrive at those equations, one must know what is the Reynolds number and how Reynolds number is used to calculate the pressure drop. So, when it comes to this definition of friction factor, so we have to now think of this definition of friction factor here. So, here we try to arrive at this for a flow through a capillary. So, when there is a capillary and a flow takes place through a capillary, there are these forces that are coming in that are existing. Here we pick up a differential element. This is if I look at the side view, this particular annular area we are referring to. So, this from the side view, this is the annular area we are referring to. So, in this if I take the front view after cutting, this is the hatched portion that we have. So, this is at a radius r, the thickness of this annulus is dr and the length of this annulus is, let us say, dx, and r, capital R is the radius of this capillary. So, now if we look at the forces that are working on this particular differential element, if we pick up this particular differential element and if we try to find out what all forces are acting here, we can see what is the area of this annulus. The area of the annulus would be pi into r plus dr whole square minus pi into r square, that is equal to pi r square plus pi dr whole square plus 2 pi r dr minus pi r square. So, these will cancel out and dr being small, since this is a differential element. So, this term is set to 0. So, you are ending up with the differential area is 2 pi r dr, that is the area of this annulus. So, over this annular area, pressure P is acting over this entire cross sectional area here. So, over this annular area, the force when you write, so that would be pressure P into area. So, this area is 2 pi r dr, which we found here. And from the other side, once again the area is 2 pi r dr from the other end of this differential, this hatched element, but here the pressure is changing with x. The pressure has to change with x because we are expecting a pressure drop because of friction. So, this on this side the pressure is P plus del P del x dx. So, what essentially what are we doing here? We are taking a Taylor series expansion. We are considering this length is dx, right. So, we are taking what the pressure here is P and here pressure is if we take a Taylor series expansion. So, P at x plus dx dx would be the p at x plus, if we take a Taylor series expansion, it would be p at x plus del p del x dx plus del square p del x square dx whole square by 2 factorial plus there would be other higher order terms. So, now what you do here in this case is you are assuming these terms are not existing, the higher order terms, only this linear term existing. Why? Because this dx is small, or in other words the pressure in x is changing, it is definitely non-linear, but you choose to assign pressure to be linear since this length dx is very small. So, this change is, I can consider this change to be linear. So, that is what the assumption is. So, you based on this you write p plus del p del x dx into 2 pi r dr, and here there would be a shear stress acting. So, here you have tau r x into 2 pi r dx. Mind it, what is the area, annular area here in this case? It would be 2 pi r 2. So, this is, if we look at this annular area, it is basically, this is r. So, this is 2 pi r, this is 2 pi r multiplied by dx. So, 2 pi r dx is now the area over which the shear stress is acting. The shear stress is acting, this is the annulus and this is the hatched area that we are working with. So, now this, as far as this part is concerned, so okay, so this r is the internal radius. So, this particular area, so we are looking at, sorry, this is not the right one. So, if this is the area, out of this we are looking at only this part. This is the radius r. So, this particular area is 2 pi r into dx. So, basically this, so this inner this part is 2 pi r into dx, the inner one, and the outer one would be 2 pi r plus dr, because this radius is r plus dr. So, outer one will also have an outer radius. So, this is 2 pi r plus dr into dx into dx. So, this 2 pi r plus dr into dx. So, this is the outer layer you have. So, 2 pi r plus dr into dx is the area, and this time it is tau r x is the shear stress at the inner wall, and here it is tau r x plus d tau r x dr. Again you are taking this Taylor series expansion of this tau and then ignoring the higher order terms, assuming that tau is linear over this small distance dr. So, in this case this is dr and in this case this is dx. So, now if one writes the sum of all these x components of forces, then one would write this one arising from here. See, p 2 pi r dr and p 2 pi r dr, they will cancel out. So, this is cancelled out. So, this x component is positive and here this is negative. So, this minus this we are talking about. So, when we take this minus this is gone with this p 2 pi r dr. So, this is left minus outside minus del p del x dx 2 pi r dr. So, that is exactly what we are talking about here. Minus del p del x dx 2 pi r dr. So, this is the term arising from this minus this. Similarly, you have positive x, we have this term, and we have the shear term here, and we have this term here. So, this is, if we sum them up, we will end up with del p del x, that is equal to del p del x is equal to these terms. So, you can the other these are some of the terms are cancelling out. For example, 2 pi will you can get rid of 2 pi everywhere. So, it will be simplified to del p del x equal to this, and this right hand side tau r x by r plus d tau r x dr, this can be combined as 1 by r d of r tau r x dr. So, you can combine these two. So, essentially you will end up with this as the governing equation in this case. I think this sign convention one should not use, because both are positive in x. So, I think this should be taken as this only, because this both we are treating it as positive. So, this is the governing equation, and upon integration, if we do the integration here, that means we are doing d of r tau r x, that is equal to, now this del p del x term we are not doing any, del p del x we are treating it as if it is a pressure gradient. So, del p del x later on we will simply equate it with delta p by L. So, del p del x, though we are writing it in differential form, this is basically a box, and that box we are carrying in down the line. So, we are basically, when we do the integration, it is d of r tau r x is equal to dr goes to the right hand side. So, d of r tau r x is equal to some constant into r dr. Basically, that is how we are treating it. This is just a box we are carrying, we are not getting into this. So, r tau r x is equal to r square by 2. When you do the integration, it is basically integration of r. So, you have del p del x, this box is remaining outside, into r dr on the right hand side, and on the left hand side you have d of r tau r x. So, when you take the upon integration, r tau r x equal to integration r dr is r square by 2 plus C 1 is the constant of integration. Now, this tau r x can be written as mu du dr. So, from this you write this tau r x is mu du dr, and this, so one r was there. So, this r is going to cancel this r square. So, it becomes only r, and this becomes C 1 by r. So, you are dividing both sides by r. So, here it is becoming only r instead of r square, and this becomes C 1 by r. So, then you have this. So, tau r x if you replace by mu du dr, so you end up seeing here as mu du dr is equal to r by 2 del p del x. Del p del x we are keeping it as a box, we are not touching anything there, plus C 1 by r. So, we have, if we do this integration once again, now what we do is mu goes to the right hand side, du dr. So, you are doing this integration on u, and this dr goes here. So, again you are doing r dr here, this integration, and C 1 by r dr. So, when you do this integration here, C 1 by r dr you have to integrate, and r dr you have to integrate here, because here essentially you are writing that du is equal to 1 by 2 mu this box del p del x r dr plus 1 by mu C 1 dr by r. So, this is what you end up with if you break this up, and when you do this integration, then you have to integrate these, and there would be a constant of integration term C 2. So, when you do this part here, this side it is u, here it is again r square by 2, r dr integration is r square by 2, and then that 2 will multiply with these 2. So, that is why we have r square by 4 mu, del p del x remains a box as it is. And when you do this here, C 1 by mu comes out outside the integration, and C1 by mu comes out of the integration, and dr by r is ln r. So, that is exactly what you see here, and C2 is the next constant of integration for arising out of this integration. There has to be a constant assigned, which is C2. So, this is the master equation for velocity profile for flow through a capillary. Now, if we proceed on this further, if we if we work with that equation, and if we apply the boundary condition that at r is equal to r, u is equal to 0, that means at the inner wall of the capillary the velocity has to be 0. That is basically no slip boundary condition, which is known as the fluid which is in contact with the wall, which is static, that fluid also has to be static. And at r is equal to 0, u is finite. Why r is equal to 0, u is finite? What is the implication of this? If we go to this equation, you can see here that if r is equal to 0, at r is equal to 0, this term becomes ln 0. So, that will make this velocity infinite. So, if you want to hold this to be finite, because at r is equal to 0, we know at is the center of the capillary, it cannot happen. So, naturally one can say that this C1 has to be equal to 0, so that this term is completely gone, otherwise this cannot happen. You cannot, otherwise this u would become infinite at r equal to 0, which is not the case, we all know. So, that is why this u is finite implies C1 is equal to 0. So, this is one condition, and at r equal to 0. So, now if you put these, so C1 is already 0 and C2 you can find out from applying this boundary condition. So, if you do that, you will end up with the velocity profile, which is given by this. U is equal to minus capital R square, R is the inner radius of the capillary, small r is any radial point, okay, but capital R is the inner radius, divided by 4 mu del p del x, again we retain it as a box, we are not touching anything there, 1 minus r by r whole square, small r is any radial point. So, this u is a function of r. So, at any radial point, this would be the velocity profile, and if one wants to find out what is the average velocity, we all understand that this u is applicable. U, when you talk about u as a function of r, we are talking about an annulus. See, at a radius r, we have an annulus, let us say, we have an annulus, and this velocity of the fluid through this annulus is essentially u at r. So, that means this, the area of this annulus we have already found out just before, it is 2 pi r dr, it is pi of r plus dr whole square minus pi of r square. So, ignoring this dr whole square term, it is 2 pi r dr. So, this multiplied by u, this gives me the volumetric flow rate, that is u is the velocity applicable to this annular area. If I am talking about, if this is the overall capillary, and if I talk about here this r is at some other r, and the velocity around that annulus, velocity of the annulus, that annulus which you draw around that r, that u would be against that particular radial distance. At this radial distance, this is the applicable u, and the corresponding annular area is 2 pi r. So, 2 pi r dr. So, this multiplied by this is velocity in meter per second into meter square. This gives me meter cube per second. So, this is the volumetric flow rate. Now, if you integrate this for all r running from 0 to capital R, that means you are doing this for all such annulus, all such annuli possible, this for r running from 0 to capital R, which is the radius, inner radius of the capillary. So, this is the, then if you integrate it, then this is the volumetric flow rate over the annulus. When you integrate, this gives me the volumetric flow rate over the entire cross sectional area. So, this is the volumetric flow rate, and now if you divide by total cross sectional area, which is pi r square, this gives me the average velocity through this cross section, and that is exactly what they have done. In V bar, which is the average velocity, is integration 0 to capital R u 2 pi r dr by pi capital R square. So, now if you bring in this u here and do the integration, it would be, then you are basically doing u into 2 pi r dr. Now, u is a function of r, here we have this functionality. So, when you bring in this and do the integration, you will end up with this expression, del p del x remains box as it is, and this integration between 0 to capital R will take you to 0 to capital R will take you to r square by 8 mu. If one does this integration as per this, so that means putting this u in here as this u. If you do this and now you do the integration, then you will be arriving at this. So, now if you, instead of del p del x, if you write these as delta p by L, in fact, there has to be a minus sign here, which we are carrying here. So, this u when we bring in, so this is anyway, this has to be minus del p del x, and this del p del x can be replaced by delta p by L. So, this delta p by L is the, so del p del x anyway we carried it as a box as if it is the pressure gradient, and now we are saying it is the finite delta p change over some length L, it is not a differential length dx. So, this is the delta p by L pressure gradient, and this, and since r square 2r is equal to d diameter. So, instead of radius you can write it as d square by, so this is to be 8 into 4 in that case, because when you square it, d is equal to 2r, that means d square is equal to 4r square. So, this 4 will go here as 32. So, d square by 32 mu. So, this is the average velocity. Now, when it comes to frictional loss, generally in fluid mechanics they call it a frictional loss. Frictional loss is given by delta p, which is the pressure drop due to friction, divided by density rho, So, what is the typical unit of this what is the unit of this expression? I believe it is force per unit volume. Okay, so this is the amount of loss that is happening. So, this delta p by rho, anyway forget about this HF. If we look at delta p, which is the frictional loss, so this delta p is basically due to friction, delta p by rho is the density. So, it is customary to divide it by rho. So, that would be equal to, if we delta p divided by rho would be, if we work with this from this expression, V bar is equal to this quantity, So, if we equate the two, we get delta p by rho would be, in that case all these terms will go to the left hand side, 32 mu L by d square will go to the left hand side, and moreover there is a rho in the denominator. So, there will be a rho in the denominator. So, that is why we have here 32 mu L V bar by d square rho, and this can be written further as, if you write this Reynolds number as d V bar rho by mu. So, then in that case one can write this delta p by rho as 64 by Reynolds number multiplied by L by d, it is again a dimensionless term for that pipe, and V bar square by 2. So, essentially this is, you can say this is fraction of kinetic head loss due to friction into V bar square by 2. So, this term, this 64 by Re is referred as friction factor. this is referred as friction factor, and so the pressure drop due to friction by rho is written as friction factor F multiplied by L by D into V bar square by 2. So, this is this friction factor. So, now we can see this friction factor is equal to 64 by Re, but this is applicable for laminar flow. When it comes to friction factor for turbulent flow, generally what people do in this case is they follow something called a friction factor chart. There is friction factor chart available for to compute friction factor as a function of Reynolds number. So, friction factor versus Reynolds number, you can see initially it comes as 64 by Re. So, F is inversely proportional to Reynolds number. So, this slope of this will be decided accordingly. So, this part F is equal to 64 by Re, and then once the turbulence sets in, typically this plateaus. Okay. The change is there, but change is not that significant. So, this part is primarily the turbulent region, and this part generally the friction factor depends on the roughness. Various values of F sub by D for a pipe, you can see there are different lines drawn, and these lines are basically for different roughnesses, F sub 1 by D, F sub 2 by D. This F psi is not porosity, by the way. This F psi is roughness, in the sense that pipe inner wall is basically it is not smooth. This is there would be roughness involved, and this roughness some pipe will have. So, how much would be this height? So, this is F psi divided by D is the diameter of the pipe. So, with reference to the diameter of the pipe, what is the height of this roughness? So, if some wall can be very rough, some wall can be very rough, some one can be very smooth. If it is very smooth, obviously the pressure drop, frictional pressure drop would be less. If it is very rough, frictional pressure drop would be more. So, that is what it indicates. So, there would be different lines, but take home message is this is a straight line following F is equal to 64 by Re, and then it is plateauing to some line. So, this friction factor chart shows nearly invariant F with Reynolds number for turbulent flow. So, this is what we understand for flow through a capillary. Now, what we have to do is we have to extend this concept of friction factor to the porous medium. We have already found out how to calculate the Reynolds number for porous medium, but now we need to extend this idea of friction factor, and how this friction factor gives me this delta P. So, the same route can be followed for flow through porous media. So, that is something I am going to do in my next lecture. So, this is all I have as far as this session of the lecture of flow through porous media is concerned. I thank you very much.